Okay, so thank you for your invitation. Today I will discuss cosmic ray extragalactic source and with a focus on galaxy clusters. Sorry. So the scientific context is that as we just hear from Dr. Paul, that cluster are non-thermal sources, and because they show some non-thermal radio emission. So you have very various structures you can find in clusters, as just mentioned. Yeah, I show you some typical example with first of all Perseus, which is a cool core, which has a radio mini halo at the center, and you have also radio contribution from radio galaxies. Here is it's a radio image, and you have the contour map is from X-ray from Chandra data. Then for a merging cluster like this one, Abel 2744, you have also more extended structure, which are associated with giant radio halo, and also radio relics, which are clearly shocks. So these are you have some data, and these shocks in particular shows an non-thermal radio emission produced by synchrotron radiation of relativistic electrons. Here is a case of a Coma cluster, which shows a spectrum which is scaling as nu to -1 around. And finally, I would just like to mention that, in fact, the radio halos and X-rays match well each other. That means that you have these relativistic electrons, which are diffusely, which diffusely populate this part of the intercluster medium, where you have also further X-rays. Okay, at gamma rays, maybe you have heard about this with the talk by Rémi Adam. Just for only recently there have been some detection. So, but for most of cluster, you are only upper limits. Here is a figure obtained by the Fermi collaboration, Fermi telescope collaboration, so sensitive in the GeV band. Here you can see on top the flux above some energy, 500 MeV. So you have different models, but only upper limits. So they show more or less consistent. And this, as soon you have different model because you have different model for the gas content. And as soon as you have the gas content, we know the cross section of the interaction to produce neutral pion, and then you can evaluate the cosmic ray content inside, and especially the pressure. Here is CR is a ratio of the pressure of the cosmic ray to the gas pressure. For a different type of cluster, you can see that you have basically this ratio. It's at the level of the percent. So, as I told you, there have been some detection recently from the Coma cluster by the Fermi telescope. Here is first there have been for one of the last paper by Fermi in 2016. There were only upper limits, but we were close to detection, let's say. So here you have an image of the contours, of an image of the gamma ray emission, and the contour are from radio, 325 megahertz, and in dashed line you have the viral radius of the Coma cluster, and they've been this is a TS map In order to have a detection, you have to have your TS around 25. So there were barely any detection there. But after 12 years of data, stacking data, there have been recent publication which shows clearly some detection and some clear power spectra, which is in fact rather hard. The index is 2.2. It has been shown that it cannot produce by AGN contribution, which could be at in the cluster, which could contribute to this gamma ray emission, but they are not energetic enough to produce such level of emission. So this is an interesting detection, which opened the door for the Cherenkov telescope array. So probably Rémi Adam told you about this. There are a lot of work done in the CTA collaboration to evaluate what we should expect from other clusters, like, for instance, Perseus. So the scientific context of this talk is, as you understood, is non-thermal content of galaxy cluster. I will discuss how cosmic rays can be accelerated in these objects. They can be accelerated by multiple ways, let's say by shocks, which can develop in normal star burst galaxies, active galactic nuclei, and large-scale shocks, as just mentioned in the previous talk. And also you can have intercluster medium turbulence, which can produce some what we call second order Fermi acceleration or stochastic acceleration. One point I would like to mention, and if I have time and end of my talk, is that cosmic rays are also may contribute some heating in the intracluster medium. Especially at the center. There are some simulations which show that. And I will mention at the end the capabilities of cluster to accelerate the ultra high energy cosmic rays that mean a particle with energy about between 10 to the 18 to the 10 to the 20 electron volt. So as I told you in this talk, I have three topics. So I will start with cosmic ray acceleration site and mechanism in cluster, then move to cosmic ray feedback, and then mention ultra high energy cosmic rays. So the mechanism of acceleration of cosmic ray in cluster are basically twofold, but there are some other. I have no time to discuss them, but basically, you have diffusive shock acceleration, which can be linked with source like AGN, starburst on the normal galaxies, and as well as large-scale shocks. And then you can have stochastic or second-order Fermi acceleration or reacceleration by magnetized turbulence. So let's start first with diffusive shock acceleration. Here is a simple, simplified picture about the process. On the left, you can see a shock front, and you have some MHD wave or scattering center for the particle, and the particles are moving back and forth the shock. Why they finally are able to recross the shock is because, in fact, once a particle crosses the shock, it will mainly see the scattering center moving toward it. And then you have a kind of systematic gain effect, like a kick by a racquetball. Each time the particle will cross the shock. Then between two crossings, the particle can also do some random walk and gain some second order Fermi acceleration process. But the dominant one is the first one, and the first order process, which is diffusive shock acceleration. It is fully controlled by the compression ratio of the shock, at least in the test particle case. I show you the typical solution you have in a shock cosmic ray distribution. So below here is a test particle solution when you do not, or the pressure of the cosmic ray is not effective in modifying the shock. But in fact, the point is that as as quite easily you can put, for instance, about 10% of the shock kinetic energy into cosmic rays, and that then would modify the shock solution itself to a kind of concave structure. Here is the shock distribution, and here at the edge of the spectrum is the spectrum of the particle which are escaping at a given time from the shock. So you see that most of the escape of the particle occur first at high energies. Stochastic acceleration is a bit different. In fact, it's the same game with a racquetball, but the point is that the scattering center now are moving in a random direction. So you have for a particle can interact with a hidden way with the scattering center or a rear on. For hidden interaction, you will get energy gain, and rear on interaction, you will get energy loss. So you have kind of racket kick in one case and racket burnt in another case. If you play tennis, you should see what I mean. So the point is that as the particles are moving faster than the scattering center, particles see more scattering center moving towards it, so you have more energy gain. This is why you have stochastic acceleration. But if you look at the evolution of the particle distribution in such a process, so if you start at T in this blue distribution, you have some particles which are losing some energy because of this racket burnt effect, but more particles which are gaining energy, and with time you are building up a power law with a square root of time. So it's a very slow process. So you need a very long time for particle to get accelerated. And this was the generic problem of cosmic ray acceleration in our galaxy. This is mostly why this process does not work, because it was too long. But in cluster, it's a different story. So moving back to cluster now. I show you some simulations. These are all simulations by Dong-Soo Ryu and collaborators in 2003, which shows so this SPH hydrodynamics simulation, which shows substructure in the cluster. Basically, you have two types of shocks. External shocks, which are close to the virial radius, and internal shocks inside this radius, and these two shocks shows a very different strength. So if you look at the distribution of the sonic Mach number of these two type of shock, here I remind you the definition of the sonic Mach number, which is a ratio of the shock speed to the local sound speed. Then you can calculate the compression ratio of the shock from this. If you assume 5/3 for adiabatic index, you get this solution for the compression ratio, and then this solution for the polar distribution of the particle, which simply depend on the compression ratio in the test particle limit. Then you see that you should expect very different cosmic ray distribution from this internal versus external. Internal, you should have a very soft spectra with index close to 5, whereas in external shock, the spectrum should be harder with the spectrum of 4. This spectrum is in momentum and P-4. It's not energy. In energy, it's E-2 or E-3. The point is also about the Mach number is that it has an effect over the particle injection. Here I show you the acceleration efficiency, which is a ratio of the cosmic ray to kinetic energy flux entering in the shock. And you see clearly, depending on the model, you have some scattering, but clearly you see that for low Mach shock, you have a very low efficiency injection of particle, which question the capabilities of this internal shock to accelerate particle from what we call the thermal pool. And we will have a talk by Pratik in the next talk. We'll discuss this aspect. Now, of course, cluster are magnetized medium. are weakly magnetized, but you have some magnetic field in. And yeah, I'll show you some slice of magnetic field amplitude map separated by 250 kiloparsec around a galaxy cluster. So MHD simulations are interesting because they show that you can have some magnetic dynamo, whose process is not fully understood yet, likely connected to the turbulence and the development of vorticity, which should induce some magnetic field amplification. I would like to mention that the typical Alphen speed in a cluster is rather small. That means that the beta plasma of cluster is rather high. It's a ratio of the sound speed square to the Alphen speed square. You have a factor 2, in fact, but it's around 10 to 100. So these are very peculiar places with respect to the interstellar medium, which the interstellar medium has a beta of the order of 1. So this makes things a bit different. Another aspect of the magnetic field, which has been deeply investigated recently for shocks, is that the magnetic field, the way the magnetic field is oriented with respect to the shock normal, with what we call the magnetic field obliquity. Here you have a sketch here. You have the shock here. The shock is here, upstream and downstream, and the magnetic field upstream has some orientation with respect to the shock normal. And it has the particles which are injected from the shock have a tendency to follow the magnetic field. If the magnetic field is quasi-perpendicular, the particle will get very difficult, will get at hard time to recross the shock. So that means that the high obliquity can quench the particle injection, and this is a well-known stuff since the advent of particle in cell simulation. Here I show you some results of a paper we recently published and which investigate this more deeply, depending on the also Alfvénic Mach number of the shock. So on the left, you have the solution for Alfvénic Mach number of about 20, and the way the effect of the obliquity of the magnetic field over the particle injection. And you see that the particle injection is dropping considerably. This is a ratio of the cosmic ray energy to the gas kinetic energy. So it's dropping quickly as you are going toward 65 degrees. But this limit angle where you can inject particle is increasing with the Alfvénic Mach number, in fact. And this is what we found. And this is interesting because in a cluster of galaxies, in fact, the Alfvénic Mach number can be rather high also. And then that means that you can inject for shocks, you can inject cosmic ray either for high obliquity. So it could help to inject cosmic rays. So let me talk about shock acceleration performance in a galaxy cluster. So as I told you, it's a low magnetization, high beta regime. So there have been several investigations in this high beta regime using kinetic simulation. Here I show you a combination of two recent work by Van Marl and our Korean colleague Ha and Ryu and Kang. We investigate the way the particle can be injected in this high beta plasma. So as no surprise, you find the same trend as I showed you before. That is the fraction of the cosmic ray acceleration efficiency is dropping as you are going toward Mach of the order of 2. And this is also verified using peak MHD simulation. And here you see a kind of a solution with a peak MHD simulation which you don't see anything occurring, whereas as R equals 4 shock, you can start to see some particle moving upstream and start to generate turbulence, and then you inhibiting the diffusive shock acceleration. And in fact, the solution found for this Mach shocks, low Mach shock, are quite consistent with the test particle solution. No, I've talked about shocks, but as I told you, cluster and as has been said before, cluster have a lot of turbulence, can have a lot of turbulence. So this is a really complex problem. In fact, the turbulence can be driven at some scales, typical scale of the order of the megaparsec, with typical speed associated with the gas infall of about 100 km per second. This makes that the turbulence regime in the cluster to be, in fact, it is, it has a sonic Mach number which is lower than 1, and an galvanic Mach number which is larger than 1, or of the order of 5 to 10. You can see this.
Sorry for the disturbance. You have about 5 more minutes.
Sorry?
You have about five more minutes.
Okay, thank you. So you have you can see the different speed here. You have the sound speed, the typical turbulence speed, and the Alfvén speed, and we are in the regime of galvanic Mach turbulence. And so usually the problem of simulation is that they are not really able to capture all the turbulence scales and to describe the cosmic ray acceleration. Another difficulty with the turbulence in cluster is that it evolves with the typical type of the cluster. Here you have different type of cluster, merging, relax, or post-merging cluster, and it evolves with the radius, the cluster radius. And you have different also sources of turbulence. So you can have the turbulence injected through this gas infall, but also AGN jets can inject some turbulence at smaller scales or higher K here. So, because this process is so complex, so people have, in order to describe how cosmic ray can propagate into cluster, they have to start with simple model using quasi-linear theory. So you have a typical diffusion coefficient which is fixed by the scaling law of your turbulence. So for Kolmogorov, you have a scaling diffusion coefficient increasing as e to the 1/3. But the problem in the cluster is that the turbulence is highly intermittent. So you can have strong spike, which can rule out quasi-linear theory. Diffusion coefficient is also sensitive to the geometry of the forcing, and you can have different source of forcing in turbulence, and it's anisotropy. And also the transport, in fact, as the mean free path of cosmic ray can be small, it can be also controlled by the large-scale motion of the gas. So simply imposing a diffusion coefficient, which is a product of the turbulence speed to the injection scale. On top of that, so I probably didn't have time to show you, but there are some, even if gamma rays observation constrained the cosmic ray pressure content to be very low, about 1% of the gas pressure, it is not excluded that in some part of the cluster you can have some higher values of this ratio, which are not resolved by gamma ray observatory. And this bring more supplementary effects of cosmic ray back reaction, so they can produce their own turbulence. So we'll skip this. So do we explain this non-thermal structure? So we have some difficulties to do it. Here I show you attempt to explain giant halos, for instance, which are things to be produced by the turbulence induced by the merging process. Here is a primary, it's likely produced either by primary electron reacceleration by magnetic turbulence or secondary electrons produced by cosmic ray interaction with the thermal gas, producing charged pions, and then which are decaying in electron positrons, which further radiate in synchrotron radiation. You have a good correlation between radio, halos, power, and X-ray. So that strengthens this assumption that you have a connection between turbulence and non-thermal emission. And most of all these radio halos are found in a merger cluster, so where you have indeed production of turbulence. But relics are more connected with shocks and DSA, but it is difficult here to explain in relics to accelerate particle from, let's say, the thermal pool because of the low value of the sonic Mach number. And so you maybe need some supply by a second order Fermi acceleration. I just want to mention an important aspect, which are external shock, because I mentioned that external shock are stronger, and but they are not really detected at radio, to my knowledge. I may be wrong, but this would be really interesting to detect them, because this is where we think that maybe highest energy cosmic ray can be produced, and the point is that these shocks are found in simulations. So here is some example of recent publication, again by the Korean colleague, which in red shows infalling shocks nearby the R200 radius. And as you can see, in this infalling shock, you can have high Mach number, as I mentioned before. These high Mach number are moving in some lower density medium, so that means that maybe they can inject less particle, but with a higher efficiency, whereas internal shocks can inject more particle, but with a lower efficiency, because you have a higher density of the thermal gas. Whatever, detecting these external shocks, large-scale shocks at radio wavelengths would be a really added value. Just to mention cosmic ray feedback, because this is what I said before, in the center of the cluster, really center. Here you see the scale, it's about 100 kiloparsec. You may expect some back reaction of cosmic ray, for instance, injected by AGN. And this has been found by this simulation by Rutkowski, that in the real center, even if on the whole budget for the cluster you may have a low pressure cosmic ray pressure, at the center it can reach values about 25% of the gas pressure. This is the black line here, as a function of time and the radius. And this could modify strongly the properties of the real center of the cluster with time, so the temperature and the density, and as well connected with turbulence generation, the entropy. Just cluster has been mentioned by Dr. Paul, is also a possible source of highest energy cosmic rays. If you put his well-known Elias plot, which equalize the size of the structure with the Larmor radius of the particle, you can do a plot in B and R space, and you see that cluster lie for the highest energy particle. For protons, they are close to the GZK cutoff, which is about a few times 10 to the 20 electron volt, because they are big, basically because they are big. And they can accelerate this particle up to high energy, and there have been some work on that, which try to explain, for instance, what we observe at the highest energy can be produced by the Virgo cluster nearby, particle accelerated in the accretion flows of the Virgo cluster. So this is a work done by our Russian colleague Zirakashvili and Tushkin. Okay, I'm late, sorry, and this is my conclusion, and if you have some question, I will be happy to try to answer too. Thank you.
Thank you very much for the exclusive review. So we have a few questions from here. Surajit?
Yes, hello?
Yeah, just one moment. Yeah.
Hello, Alex. This is Surajit here. Nice talk. Actually, thing is that you told that high number shocks are efficient. I also agree with that. Obviously, they're efficient. The thing is that due to very low density in the outskirts of the cluster, that could not produce as much as, the gamma ray flux that we need to detect, right? But what can be the, we should go for the effective Mach number, which produces more flux of cosmic rays, and which has been found like 3.5 to 4.5 Mach number. I published a paper in 2019. Also, Huang sometimes back published a paper which shows the most effective Mach number in clusters are around 4 or so, 4.5. So, have you checked what is? Because if you want to detect them, then we should go for effective, not the same one.
I'm not. So I have understood about the subject, but I've not fully understood the question. But so you mean that in fact this is this kind of balance between low Mach shocks and high Mach shocks. That is, and low Mach shocks will inject less particle, and high Mach shocks will inject more. That's correct. I'm sorry, the sound is not so good.
No, the thing is the opposite. More particle you will get in the cluster, inside the cluster, right? So low Mach shock will get more particle to accelerate. So effectively low, not really low, it's like around 3 to 4 Mach number shocks will be more effective in accelerating more particles, number-wise.
Okay. Yes. This is what I've tried to say here is, in fact, okay, you have low Mach shock, but they are moving in a higher gas density. That means that if you compare, in fact, what is important is for cosmic rays is not really the let's say the pressure or the energy, and so in the at shocks you have you can put some cosmic ray pressure. You can put a fraction of the kinetic energy of the shock. So the kinetic of the shocks is a rho, the ambient density, times the V shock square. Of course, V shock square is smaller, but rho is higher. So all in all, what is say is that I tend maybe to agree with you that maybe this effect is stronger finally to inject more particle at the low Mach shock in the cluster center. Yes, I'm not sure I've been really.
No, I wanted to know that whether you checked it, like did some statistical studies that which Mach number is more effective and the range of Mach number is more effective in cluster. I found
okay.
3.5 to 4.5. That's why I asked.
That's maybe good, yes, because so do you think it's maybe also connected? So this was a whole simulation, let's say. So maybe with a better resolution, you can have also, because there is some difficulties in simulation to capture the shock and to evaluate properly their compression ratio and the Mach number. So yes, some caution have been taken for this from the simulation, what you get from simulation about the exact Mach number of the shock, because you have a 3D shocks, so it's not easy to reconstruct a shock in 3D in simulations.
Yeah.
So maybe.
Okay. Any other question from here? Anything from online?
Yeah, I can just ask a quick one. It is about.
Sorry.
Yeah, hi Alexander. Just wanted to know
Yes.
what is the resolution you're using for those simulations that you showed. You talk about internal shock in the cluster as well as the external ones. The internal ones are the ones that we observe at radio wavelengths and saw those Phoenix regions that we talk about. Is it the same? Is it something different? What you people are taking into consideration with your simulations? And what is the resolution of the simulations when we're talking about those shocks? Yeah, this one.
This one, so you can see it. It's sorry, I do not have it in mind because it's not my work, so it's difficult anticipate, but you can see about the structure. You see, so you have a typical megaparsec scale. So it's I think if you want to really have a good resolution. At this time, it was about, let's say, I don't know, but about a few tenths of kiloparsec, let's say. And of course, it has improved since, especially with adaptive mesh refinements techniques. So I don't get the first part of your question, sorry, about external shocks.
Yeah, what's the origin of the internal shocks? What is the origin for the internal shock?
You see here I put, yes, internal shocks are possibly associated with the merging process. So you have some strong interaction. They cannot have a very high Mach number, because you see that at least the turbulence in this cluster is at low sonic Mach number. So, but possibly you can have I don't know exactly the way you can produce them. It's not so clear. You can have because the structure is very intermittent. So these are mean values, but you can have some particular places if you look at this kind of structure where the sound speed is a bit lower, and then when you got the turbulent motion can get supersonic and can trigger some shock structure. It's not yes.
Anyway, it's a very good review talk. Thank you very much, and putting in the observation and statistical data along with the simulation. So that's a really great material to refer. Thank you.
Thank you.
Long live India and France friendship.